Thank you very much for giving me the opportunity to present our work, which is on past hydrology changes on North African realm. And it is based on speleothem research. So we use cave deposits to infer changes in hydrology in the North African area. And it's a team effort. So I want to acknowledge all my co-authors who are involved in this project. The work I'm presenting today follows and continues previous work that we've done on Libyan stalagmite that's recently published. And this work was done in the Cyrenaica area, which is a coastal part of northern Libya, and inferred past hydrology changes in the last glacial period. However, speleothems record very local changes or environmental conditions. So to say more about regional scale, we need additional sites. So we continue our work in Tunisia, 2 sites. Oops, oh, that was wrong. So one on the east end of the Atlas mountain range in the Dorsal, and a second site further south, closer to the Shot area, so that is then the transition zone to the desert. So here's an example of what we found and did in Libya, so that we used stalagmites, and the cave site in Libya was dry, so just the presence of stalagmites indicates previous wetter conditions, and in that case we found 3 main episodes here, which are the more whitish parts. That's when this long 1 meter stalagmite mostly formed. So there were 3 phases, 1, 2, and 3, around 62, one about 52, and the other around 36,000 years ago. And my colleague Mike Rogerson will give you an update on the latest results on this stalagmite in the next talk. I'm now moving on to Tunisian cave sites with the 2 sites, Grotte de la Mine, which is here in the Jebel Serj. This is previously the only speleothem record from North Africa has been published from that cave 10 years ago by Dominique Gentil and his team. They found a stalagmite that formed the last deglaciation into the mid-Holocene. And the second site is here, close to the Shot, which is around here. The cave site is called Damouz Robben. On this, you can see that we are moving towards the dry zone, so we can compare 2 different hydrology areas in Tunisia. So this is what it looks outside Grotte de la Mine. It receives rain, around 400 millimeters per year. There is some not dense vegetation, but there is vegetation, mainly shrubs. And this is reflected in the cave. There is water infiltrating, so we have active formations. It is a big decorated cave, and this is a scale. This is, I think it's Mark. And we were able to collect 5 stalagmites from this cave, including one very nice, over 80 centimeter long candle-type stalagmite, which is ideal for our work. But we also had these other 4 specimens. And we used uranium-thorium dating to find out what was the time when these stalagmites formed. So here are the pure dating results on these 4 specimens. And this here, the number 2, that's the candle-type stalagmite. We spent most of the time on analytical work on this so far. But this formed in, episodically 3 phases. We have isotope stage 9, 7, and 5 in this stalagmite. So this formation is mainly during MI7 here. And interestingly, 3 other stalagmites only formed also during stage 7. So this, from this perspective, seems to be quite wet. However, it could also be a sampling bias that just by accident we only got stalagmites from that phase. The 5th one formed during the last glacial period here and also partly in the Holocene. So this one we focused on. We also analyzed for stable isotopes because that is going to tell us what kind of precipitation we have and where it's coming from, potentially. So here are oxygen and carbon isotopes for the stalagmite based on a time scale. In red is the oxygen, so the values are between -5 and -7 largely. And we can see here, this is the stage 9C. We have then here the peak, the 3 peaks, 7E, C, and A. And then we have the 5E stage. The carbon, when it gets light, indicates wetter conditions. So we think that here, at least stage 7C, 7E, and well, here it seemed to be wetter after stage 5E. But we infer that these were wet periods in that part of Tunisia, and the rain, the signature here excludes that it's going to be sourced from the south. This has to be Mediterranean-sourced water. So we don't have an African monsoon precipitation, but precipitation that's linked to the Mediterranean. So how does it now look when we go further south, closer to the desert? This is what it looks like outside Damouz-Roben. Very dry area, almost very, very little vegetation. And inside the cave, it's bone dry. There's no sign of any water whatsoever coming into that cave recently. But we do find decorations. So there are column-like that are broken. We didn't do this, so it's not our fault. We have flowstones, and we have very little small stalagmites. So what we did is we collected these broken fragments from the column. We collected parts of a flowstone, and we drilled cores from these small stalagmites just to find out what was the time when these formed, because just the presence of those indicates it was wet enough for recharge in the epicast system to allow speleothems to form. So this is a typical sample. The flowstone is about 2 centimeters thick. We have 2 pieces, and there are 2 faces. This is what a fragment looks like. It's about 5 centimeters in diameter, and these are typical drill cores with a 7 millimeter diameter. We have them between 1 and 6 centimeter long, and we also dated those. And this is the dating results by the different types. So for the flowstone, we find that these are, well, okay, this is, okay, I have to do without. The flowstones formed largely isotope stage 13 and 11. Uranium-thorium dating gets less precise when we are moving towards the 500,000, 600,000 years. So there is some overlap, but for one of the 2 flowstones, there was a clear difference between the top part and the bottom part. So we have these 2 phases. The drill cores formed also episodically. We had some that fall into the large range MIS 11. We have stage 9. Very little from stage 7, just 1. That was the wet part in Lamine. And then we also have some from stage 5. The fragments we collected formed late stage 5 and also into the last glacial period. That's the wet phase we found in Libya. So very interesting is that if we now compare the growth in the 2 sites, so then we have at least some parts where we have formation in both. Now the question is it the same precipitation source that gets into that area? So we analyzed the drill cores also for stable isotopes. And here on the bottom you can see the compilation of the drill core data put together by dating. The uncertainty on that is still quite large because it's mostly defined by bottom and top edge of the drill course. So there might be one or other peak still moving around when we continue this work. But what we can tell already is the oxygen is a little bit lighter, which is expected with a continental effect if the rain comes from the Mediterranean southwards. And it's not light enough to be monsoon, because then it would be much more depleted. So we think it's the same precipitation regime, and some of the features could indicate similar peaks, but the record for Damus Robin is not continuous enough to compare the two records in much more detail. Anyway, to summarize, the speleothems in Tunisia, in two sites, north in the middle, I mean, and close to the desert, indicate wet periods, mainly during the interstate MIS 9, 7, and 5, but also during the last glacial period. And we think that it is a Mediterranean precipitation source that makes this desert zone wet at this time. More about the interpretation of our stable isotopes is going to be presented by my colleague, Mike Rogerson, in the next talk. Thank you very much.
I just want to know, why did you assume that oxygen 18 is a proxy for rainfall variability from the beginning? I mean, it's possible that there is the effect of temperature or change of moisture source or something.
Well, oxygen, of course, is affected by a variety of different parameters, like amount effect, fractionation in the cave, but for Libya, we have mainly the source as the variability in the source of the water that makes the big changes. But it's the fine structure has various possible drivers, yes.
Very interesting records. I was wondering, I have noticed that you are missing termination 2, termination 3, and I'm not sure about 5. For some reason, terminations are missing. And it's not the only place. I mean, we are missing termination 2 in other sectors of the Mediterranean. Do you have any impression about that? Do you think you are really missing, it's just arbitrary, or there is a reason why these terminations are missing in the record?
Yeah, it's always the problem with absence of evidence. It can be a sampling bias, it can be real. I can't really tell why it's not present in our data set yet. It may occur when we, when we sample additional speleothems, but maybe it's real. But just from not having it, we can't infer anything, to be honest.
Okay, morning everyone. So I shall pick up where Dirk left off from last talk, and it's most of the same team, a few other people, and also multiple funders to consider. It's been quite a lot of hard labour gone into these records, so everyone's role needs to be recognised. But this is the Libyan site that Dirk presented that we're talking about now. It's Susa Cave. There it is, you can see on the left-hand side of that screen. It's a little hole high up in a cliff face, but within sight of the Mediterranean. So it really is a coastal site. It is right on the edge. The vegetation's pretty thin, but it is there, and you can get a quick snack if you're lucky, you go the right time of year. These strawberry trees do give you a little bit of an opportunity to refresh during field work. But it's there in easternmost northern Libya. It's part of the Jabal Akhdar, the Green Mountain. It's a relatively humid part of the world on a Libyan scale, but right in a great lacuna of information paleoclimatologically. There's quite a lot for Europe, Morocco, into the Levant. There's very, very little there in the central Mediterranean. It really is quite a gap in our knowledge. This is the same chronology Dirk just presented for this stalagmite, so I want to emphasise this is just stage 3, maybe just into stage 4 we're seeing here, from around about 67,000 years to about 30,000 years. When this record was first published, I noticed this comment come up on Twitter. The person who did the chemistry for the 116 plus uranium thorium dates of this paper deserves so much credit. I think that's absolutely true, and it was quite nice to see the international community recognising that. Obviously that was our last speaker who put that hard labour in. Having got that chronology in, though, we wanted to go further and see if we could take something about the process of rainfall supply into this area out of this really interesting record. There are these growth phases embedded in that data set, which are the very dark grey vertical zones on that diagram there on the left-hand side. Two of these, 1 and 3, appear to be precession related, but the middle one, phase 2, appears to be obliquity related. There are also shorter phases which sit on the Greenland-Dansgaardurske interstadial, sorry, that's a mistake on my slide. And Mark and Christoph have done really good work sort of generating these isotope data that we can use to go on. But while we were doing that work, we noticed fluid inclusions in this stalagmite. And with Yuri Dubliansky, I've been trying to crack open those fluid inclusions, track between and within crystals within the stalagmite, to really look at where the rain was coming from. So rather than just saying it was wet, we're trying to say it was this rainfall system that was causing the change in our climatology. The problem we hit almost immediately, actually, if you look at the previous image, you can see this. There's more than one population of inclusions. There's these little small ones that just give you a sort of black-grey appearance to areas of the stalagmite. And there's great big craggy black ones as well, really quite big inclusions. And we didn't realise initially how much of a misery that was going to make for us. But there was almost no relationship between the amount of sample you put onto the instrument and the amount of water you get to analyse. So that was really making life very difficult. Just to combine with that, with there being two different populations of inclusions in there, what we were analysing would be a variable mix between those two populations of inclusions. Replication became very difficult. We also found that particular fabrics had water and other fabrics did not have water. So even beyond the basic problems that we had, we ended up with only data from parts of the record. And these really are into those three main growth phases, were the only parts of the stalagmite with water in it. This means essentially that from a time series data set, there isn't very much we can do with these inclusions. They're going to tell us about the process, but not very much about the changes of process through time. There was very little consistent pattern similarity between the D18O in the drip water within the fluid inclusions and the D18O of the carbonate they were deposited with. And that confused us initially. There is a relationship, however, with the deuterium. And when we got into analysing the data set, it became clear that this was quite a complex system, but was tractable to analysis. And what I did to try to understand this, I thought, okay, I'm going to roll right back and just think about what the rainfall isotope controls are. So I went back into the GNIP datasets and got out the three closest large datasets within the GNIP system, which is Tunis, Sfax, and Bet Dagan over in the east. And when you compile all the data from those three GNIP sites, you get the plot you can see in the top left. There's data all over there. There's loads of data to work with. But the key thing you take from that is there are two different isotope fractionation pathways in this data set. There's the global meteoric waterline type behaviour, which you see mostly in Tunisia. There's also the Mediterranean meteoric waterline behaviour, which we're seeing at Bet Dagan in the Levant. And that's very interesting because you then start thinking, well, okay, so Cyrenaica's in the eastern basin, so are we going to be in that western type or that eastern type of rainfall behaviour, or are we going to be split across them? Bottom right, you can see the little TIE fighters that show each individual fluid inclusion isotope measurement. There's quite a lot of them. There's about 56 measurements shown in there, and they really give you a big cloud of data. Now, I've only shown the global meteoric waterline there as those tram lines on the screen, because I want to really emphasise that you really cannot explain that data set either with a global or a Mediterranean meteor waterline. That data set is clearly telling us that at least at different times, there were both types of rainfall active and supplying water into this system. And that's a really interesting result, because that means that this is probably why the calcium carbonate behaviour is complicated for us. Going back to the question that was put to Dirk about the oxygen isotopes, this is not a simple data set to analyse. But what's really exciting is the way that the data sits directly on the modern precipitation isotope behaviour. It means we can use those modern precipitation isotope behaviours to actually deconvolve that signal and work out what's going on at different parts of this record. For the real hard asses out there, we did manage to replicate some of this data, and even within that subset of properly, fully replicated data, you still can't explain this behaviour with a single moisture source. This is definitely 2 moisture sources involved in this data set. So I just thought I'd make the most complicated diagram I could, so here it is. And what I'm trying to show in this diagram up here is that you can explain most of the variance in this data set essentially between the big white circle and the little grey square on the right-hand side and the left-hand side of the diagram. Now, the little grey square is the most rainy months in the Bet Degan record. That's when the Levant really starts to get very, very humid, very moist in the modern climatology. The big white circle is what's called the Mediterranean source rainfall at Sfax. Now, that's water that's being effectively evaporated from the western Mediterranean, advected east into the central Mediterranean, and then precipitating onto Cyrenaica. Both of those moisture sources are internal within the Mediterranean. And that's perhaps the most impactful conclusion of this record, is this is not external moisture from the Atlantic getting into the Mediterranean and altering the large-scale hydrology of the system. This is internally recycled water within the Mediterranean system that is not going to show up in a marine water budget type calculation. This is merely transporting masses of water within that single drainage basin. That's quite significant, because that means that these coastal records of rainfall may not be a tractable basis to start judging things like the sapropel behaviours from the Mediterranean marine system. That would have to be an external water source. It also means that we have at different times, at different rainfall events, a different mixture of this eastern type rainfall and this western type rainfall within the system. And that's probably quite important as well, because they are quite different rainfall type behaviours. There is a tendency for the data to also move down that global meteoric waterline trend, down towards the white square, down in the sort of lower part of the data set. Now, that is the part of the data where you're getting Atlantic water mixed into the system. A simple kind of back-of-the-envelope estimate would be about 10% addition of Atlantic water is showing up inside this record. So there is some external water, but that's not what's controlling the bulk of the humidity behaviour. If you think about the east and the western water, one of the characteristic differences between them is the deuterium excess. The re-evaporation and water cycle in the eastern Mediterranean drives a relatively high deuterium excess for that particular part of the data set. And when I was looking at that previous plot, I noticed that phase 2 tended not to get up into that Bet Degan type behaviour. It tended to be stuck on the Tunis type behaviour. So you can see this here, the little blue crosses, and actually there's some blue crosses I've just realised are hiding behind the black line at about 51,500 years ago. All of that data clumps in that lower part of that deuterium excess diagram for the fluid inclusions. And that is quite important, because that means that eastern Mediterranean type of rainfall is not active within Cyrenaica during that phase 2 behaviour. So despite the difficulty creating continuous time series in this data set, we are getting a sense of time variable behaviour within the system. So a sort of summary of what's going on with that in terms of the interpretation would suggest something like this. We have phase 1 and phase 3, which are forced by precession. And what we're seeing there is higher convergent rainfall within the eastern Mediterranean, which is probably relating to a north to south squeeze of the atmosphere due to a northward motion of the ITCZ. And that's generating this deuterium excess bearing type of rainfall. And in all 3 phases, we're getting these westerlies drawing water in, probably in the winter, probably relating to Atlantic storm tracks. But I want to reiterate that most of the actual water that we're seeing is not Atlantic water, it's water that's evaporated from the western Mediterranean basin, then being reprecipitated into the eastern Mediterranean basin. There's probably quite a lot of significant impacts of that, particularly if we have a very significant transport of west to east moisture. Looking at an eastern Mediterranean humidity anomaly type data set might lead you astray. That might show you something about the degree of transport within the basin as well as the net system behaviour. But certainly we have these westerlies are very important in all three phases, and the convergent rainfall in the eastern Mediterranean only seems to be active in the precession peaks. We've long debated the amount effect. You can really see an amount effect in Tunis, but it's essentially, does that data go down in that direction? Well, are we seeing these very negative isotopes reflecting high rainfall amount in this Libyan record? Not very clearly. So if you look at the absolute magnitude, particularly of the calcite behaviour in these areas, there's no consistent behaviour there between the growth rate and the isotopes. That's a little bit disappointing. That's reflecting the source effect, essentially. What we do find is that we tend to see the same behaviour repeated in the carbon isotopes. So potentially, we may be able to back out amount from secondary measurements, the carbon isotopes and the trace elements in this record. So watch this space, there's more to be learnt. That's a summary of it, but I've spoken too long, and I'm completely out of time, so I'll run straight to questions and comments.
We have similar data in Israel, but I think you haven't considered the fact that in the past there was summer rainfall events. Other data, which I can talk to you later about, indicates that there was an effect of the Atlantic from the southwest at certain periods, 3, 5, and parts of 7, coming in during the summer. Most of all rain today comes only in a few major storms during the winter. This is from the Mediterranean, of course. And I think your mixtures, we see this. We can separate it out very nicely when you have two sources. And if you consider the summer rainfall, and I don't want to go into more than that, but we do see this. Thank you.
It did cross my mind that we may be seeing a seasonal difference, particularly with those deuterium excess type numbers. I chickened out, and I couldn't quite be confident that I could say that from our data. And it's quite a long way from Libya up to Israel. So I suspect we are seeing something like that, but I'm too much of a coward at this stage to go to the cross on that argument.
Shows that the Nubian also came in during the summer, during these past periods, and you see very clearly the difference in the deuterium in the water itself. Thank you. Mm-hmm.
So I'm going to present mostly data on climate and environmental conditions during the neolithization of the Carpathian Mountains. And it all started with this map. And when I saw this, it caught my attention, this part here. This is the Carpathian Mountains. And, okay, why do we see this? Why do we have this, moving people around? And if you put this map, so it seems that people traveling from the Balkans reached the southern part of the Carpathian Mountains and then moved westward and then just around the Carpathians, and they got in the inner part of the Carpathians in Transylvania only maybe something like 1,000, 1,500 years later. So we wanted to have a look at this to see what happened. Is it just an artifact? Is it real? Did they got inside the Carpathian Mountains at a later date or not? So to do this, we have looked at paleoclimate. We used speleothems. We used ice caves, a summer record from chironomids, and precipitation data from north. So we looked at temperature, precipitation. We looked at amount of precipitation and the source, vegetation changes, and floodplain processes. The idea being that these people, they were moving along the floodplains looking for areas that are suitable for agriculture. So these are the areas that we investigated for fluvial processes. Okay, so the data for precipitation, we use the data from Feordean et al. Published. We use this record, pollen-based, because it was the only precipitation reconstruction that we have for that area. And then for summer temperature, we use the recently published data set by Monica Todt in the Holocene on the southern part of Carpathians, chironomid-based. And for winter, we used the newly published ice core record from a cave. This is the Scarishara ice cave, where we drilled the core. I will insist a bit on winter climate because it's different. So we drilled the core, something like this is the ice block, a 22-meter ice core, and we radiocarbon dated it and then did stable isotopes for climate. This is the depth age model, and this is the reconstruction. And it was very useful that we could reconstruct both the temperature. This is the temperature record going from 10,000 years towards the present. And because it's ice, we could use the oxygen and hydrogen to calculate the deuterium excess. And we interpret the deuterium excess as an indicator of the source of moisture. So this is the deuterium excess record, which can, with low values possibly indicating a wet or cold source, whereas higher values indicating a warm, dry, evaporated source. Or as you've seen in the previous talk, possibly Eastern Mediterranean source of precipitation. So, yeah, this is the interpretation. I will skip this. I will get to this one. I pulled the data together. So we have a winter temperature reconstruction from 10,000 to the present. We have a summer temperature, annual temperature. This is pilotem-based, precipitation amount, and this is precipitation source. So you can see that there is a strong contrast between winter and summer conditions. So the early Holocene winters were very cold compared with the summers, which were high, warm. And then winter started to warm towards the mid-Holocene, and then slowly to cool down towards the present day, the past maybe 1,500 years. Contrary, summers were very warm, and they started to cool towards the mid-Holocene. And if you look at the annual temperature reconstruction and the winter, you can see that the annual temperatures are mostly controlled by changes during the winter, not during the summer. We are still playing with these things. We want to understand exactly what does it mean in terms of reconstruction for other parts of the world. How much of the annual, usually annual and summer reconstructions are pulled together, but it seems that at least here, it's winter that is controlling the annual. And then the precipitation, again, a maximum in the early Holocene, lower values in the mid-Holocene, again, increase towards the end. And this is the moisture source. We put a threshold around here, and we think that lower values indicate mostly Atlantic source, and the higher values probably Mediterranean source. And you see that this curve is somehow fitting the precipitation curve. So then what we did for the early Holocene, before the arrival of the Neolithic peoples in the area, it was cold winters, hot summers, so it was a strong seasonality, and it was also wetter. This is the time when Neolithic people started to move in the area, and you see that winters became milder, whereas summers became slightly colder, so it was a decrease in the seasonality, and it was somehow drier. And yeah, this is the present when it seems that we see a return towards the conditions similar to the early Holocene with a strong seasonality between summer and winter, but yes. Okay, so this is that I would like to keep you in mind. This is the period we are interested in. And then for the same period, we look at the vegetation changes at different altitudes. This is from the low-lying, this is something like 200 meters above sea level going up to 1,800. We were interested in this period, but we don't see very much change at this time. And this is just to put it in a different way. So at this point, we think that maybe vegetation changes were not influencing the peopling of the Carpathians. Maybe people were influencing vegetation, but this is work that we are doing now, so it's not yet finished. What was important for us, more important than vegetation, was the floodplain processes. Because the forests, the hills, the terraces were all forested, so the only possible avenues for people moving inside the Carpathians were along the main valleys. So we focused our attention here in Transylvania, and we also used we used some data from these regions. I'm not going to go into details. I will just show the kind of work we did reconstructing. So we were interested in looking at how the floodplain looked like. Basically, we wanted to understand if the floodplain is suitable for agriculture. Is it dry? Is it wet? How the how the rivers are flowing? Is it a braided river or is it just meandering? So we wanted to reconstruct dry or wet phases for these rivers in different parts of Romania. And I will just show you maybe the conclusions. So it seems that around this time, it was a change in the style of river behavior from a mostly braided behavior in the early Holocene with multiple channels occupying the entire width of the valley towards a more meandering style around 7,000 years when there is one single channel and the remaining of the floodplain was mostly dry for tens of years or maybe hundreds of years. Basically, the floodplain was not devoured on an annual basis by the channels, but maybe on a multi-century scale. So it was more stable. So if you want to put an overview of this, we think that after around 7,000, most probably, it was a reduction in the seasonality and the degree of continentality in the Carpathian region. Precipitation decreased, so it was much drier. We don't know anything about vegetation. It was this shift in river styles from braided to meandering, leaving the floodplain dry, ready to be used. And also because of the reduction in precipitation and the reduction in Mediterranean precipitations, we saw a drop in the torrential activity on the slopes. So basically, it was the edges of the floodplain were no longer devoured by torrents coming from the slopes, so they could be used for vegetation, for agriculture. So this is we think that is the moment when people started to see these valleys crossing the Carpathians as good for agriculture. So I put this here, not before, because I have solved everything. So it's a map of loss distribution. And you see that it's less here and it's less here. So if you remember the first image, people were coming here, and they found this dry and drained area. So they were suitable for agriculture. They moved towards the Pannonian Basin, again, with dry areas. But they didn't enter the inner part of Transylvania because the floodplains were still muddy. There was no loess that could be used for agriculture. So it was not a very good area for agriculture. It took something like maybe 2,000 years after they reached this point that the conditions changed so they could enter this part of the Transylvania. So this is just a map of how they started to people. It started most probably before 7,500, we see no Neolithic people in this area. And around our paleoclimate data shows that conditions started to change after 7,300, started to become drier. So yes, people were just spreading all over the place. And I go to the conclusions. We think that sometimes after 7,300, so first Neolithic people arrived in the southern part of Carpathians at around maybe 8,000 BP. It took them another something like 1,500 years to get in the inner part of the Carpathians. And we think that the barrier was the floodplains that were flooded on a regular basis and high torrential activity, preventing them from having agriculture in the floodplain. And only after climatic conditions led to a change in the river styles, they were able to get in the inner part of the Carpathians and settle Transylvania. So yeah, that's the last slide. Thank you.
Hi, that was a very interesting talk. I just have a question about the abrupt events that happened during the Holocene. So did they have any influence on the archaeological occupation in these regions? For example, the 4.2 kiloyear event has been talked about a lot, and it had influence on the Mesopotamia and the Egyptian, and also the Indus civilization in India and Pakistan. Do you have any influence of those sort of events? The 8.2 kiloyear drying event is also, did you see any peculiar changes in the climate record and the archaeological occupation?
I would say no. This is because, first of all, we don't have too good control for the archaeological phases. It's only maybe 40 C14 dates. And the other thing is that we don't see the 4.2K event as a change in temperature. We tentatively think that we see it as an increase in Mediterranean precipitation reaching our site. Nothing happened in terms of temperature, so it didn't become colder or hotter or something like this. We only see, maybe, but it's very tentative, maybe an increase in maybe there was an increase in Mediterranean precipitation at that time. But we don't know how to explain this yet, so I don't know. Otherwise, we didn't see any change, so any influence on the people living there, like very short scale things.
Hello, so I have a question about your oxygen isotope record from the ice in the cave. Mm-hmm. You said that the deuterium excess somehow tells you anything about the direction where the moisture came from, but the other opportunity is that you have sublimation, that part of the ice evaporates. So how can you prevent that? Your delta 18O record is biased by these processes.
Sublimation, you mean like from solid to vapor?
Let's say evaporating water from the ice.
It wouldn't affect the isotopic composition of the ice because of the very slow the speed of the molecular diffusion is very slow. So, and the ice forms by the freezing of water. So we would rather worry about the kinetic processes during the freezing of water that are affecting both isotopic composition and deuterium excess. And we spent a couple of years monitoring the cave just to see, collect precipitation outside, drip water in the cave, ice after it froze. And we were comparing to see the best method of how to get the climatic signal out of the isotopic value. And it's two different methods, and we compared, and it's working. So based on 5 years worth of data, we know that we can get the climatic signal out of the isotopic composition. And it's evaporation, it won't affect it. Sublimation, because of this, it's a solid, it's a crystal, so it's not changing that much during sublimation. It's not like snow where you have problems. It's solid ice.
Good morning. Today I'm going to present you some preliminary results from this informal project called CALMA, which aims to explore the potential of Macedonian caves as paleoclimatic archives. It is, in a broad sense, a side project with respect of the ICDP Scopscope project, which investigated in details the last 1.5 million of years of climate history preserved in the sediments of the Lake Ohrid. The ICDP Scopscope project has already produced a 633 kiloyears long record of detailed climatic history, which represents like a benchmark for the regional climate that can be complemented by the speleothem record. So the climate in the area is Mediterranean, but with continental influences. Moisture availability is linked to the penetration of westerly storm track and also to local cyclogenesis within the Mediterranean. There is an influence of large-scale atmospheric patterns, such as the North Atlantic oscillations, and it's possible to observe a negative correlation between the winter precipitation and the NO index, as already observed also for Central and Western Mediterranean. The cave where the speleothem was found is located in the watershed of the Lake Ohrid. Okay. It's located in the watershed of the Lake Ohrid, and it opens at 1,130 meters above sea level. More close to. Okay, sorry. And it is now the cave is now fossil, and it has a wooded catchment. And here is the stalagmite. So it is mostly composed of elongated columnar calcite, but it has also a basal interval of aragonite, showing a crystal ray habit. Both these fabrics indicate usually a deposition close to the isotopic equilibrium. This sample presents two growth interruption, one here between the aragonite and the calcite, and another one here between two sections of calcite. And here the age models, which is still ongoing. With the actual dating, it is possible to say that the first growth interruption, it's very short, was probably very short, and so it is possible to define two main growth phases, one between 330 and 290 kiloyears, and one between 260 and 245 kiloyears. Uncertainties are still quite high, but we are further dating is ongoing to reduce these errors. So the record broadly covered the MIS-9, the stage 9, and part of the stage 8. And the MIS-9 is quite an interesting period because it is poorly represented in the spiritum record, and it also was characterized by particularly boundary conditions. Indeed, it has the highest atmospheric CO2 concentration of the pre-industrial, and it was also characterized by a particular orbital configuration with high obliquity and a particular insolation pattern with strong summer insolation over both poles during the substage 9E. This period has also been investigated by joined marine and pollen record from the Iberian margin, and it has been shown that it was characterized by a variable phasing between terrestrial and marine substages, as already observed, for example, also for the stage 5, but with a different pattern. The MIS-9 also appears to be characterized by a significant millennial scale variability. And here is our stable isotope record. A few words on the aragonite. Its deposition usually in spiritum is related to drier conditions, and when the precipitation occurs close to the isotopic equilibrium, there is a quite fixed offset between aragonite and calcite. These different fractionation factors between aragonite and calcite are quite well known from experimental and field studies, and so it is possible to correct the aragonite delta 18 values, the aragonite delta 18 values to bring them in the range of the primary calcite. On the contrary, this simple translation is not recommended for the delta C13 because the offset is highly variable. So here is the record again with the corrected values, and it's possible to see that there is quite a strong variability both on the orbital and on the millennial time scale. But what drives this variability? So here I've reported just a few examples on how the delta 18 of spiriums is interpreted around the Mediterranean and the Europe, and just very few from the Holocene and the last interglacial. And it's possible to see that there is like a spatial pattern with spiriums from the Alps and from the Central Europe mostly respond to a temperature signal with lower values related usually to colder conditions. By the contrary, in the Mediterranean, the delta 18 is more related to the hydrological pattern, and there is a predominant influence of the amount of precipitation with lower values related to wetter conditions. Obviously, there is also an overall influence of the source of the precipitation. Indeed, the changes in its location and composition can affect the meteoric precipitation and also the spiritum record. And this effect is particularly important in particular settings like in the Eastern Mediterranean or during particular moments such as during the glaciations. A clue on how to interpret our delta 18 record came from the comparison with the lake record, the Lake Ochrid record. Indeed, it is possible to see that there is quite a good match between our delta 18 record when it is interpreted in terms of amount effect and the lake record. Indeed, here I have reported just a few proxies from the lake. There are pollen with increasing concentration related to increasing temperature and humidity. There is the potassium record, sorry, here there is an error. There is the potassium record, which is related to catchment erosion. There is the total organic carbon, which is related to the primary productivity. And there is the total inorganic carbon, which is related to the primary productivity, but also to the runoff, which supply ions to the needed for the precipitation of the calcite within the lake. And so it's possible to observe that there is quite a good match with our record. And so it's possible to define a local environmental framework. Indeed, the mineralogical changes between the aragonite and the calcite and the decreasing trend of oxygen values match the increase in precipitation after the MIS 10 to 9 transition. It is also possible to observe a comparable length of the terrestrial interglacial optimum. The wettest condition of our record match the increase in pollen and in other proxies indicating the runoff and the primary productivity. There are evidences for an increasing variability at the millennial scale during the glacial inception. It's a substages 9D to B. And there is a prominence of the interstadial 9E, which is characterized in our record by wetter conditions, which are also reported in the lake record. The growth interruption observed in our speleothem match the driest and colder condition during the MIS 8C, whereas the growth restart again during the interstadial 8B, which is also characterized by increasing precipitation and increasing pollen. And here the carbon record. So usually in temperate setting, it is usually related to the supply of organic CO2 from soil. And in our case, values are always, it doesn't work, are always relatively low, indicating that this supply of organic CO2 from soil related to soil and vegetation development was quite well developed also during the glacial inception. Interesting is this period of, this peak of anti-correlation between wetter condition expressed by the oxygen and positive carbon values, and it may be related to high infiltration rate. Indeed, when there is a high infiltration rate, the water is equilibrated with the soil CO2 and thus can retain an isotopically heavier atmospheric signal, causing these positive values in the carbon. Also interesting is the decreasing trend which we can observe after the growth interruption. Indeed, it can be related to the progressive soil development after the maximum of glacial MIS 8. And here some preliminary comparison on a regional scale. For example, here I have reported another speleothem record, which is still ongoing. Also, this one is still ongoing, from the Corchia cave in central Italy. Also, the delta 18 in Corchia is, at least during the interglacial, interpreted in terms of Haumont effect, and it's possible to see that although there are still some chronological mismatching, there is quite a good match both for the orbital and the millennial scale variability. And this is important because both these two records are independently dated. Also interesting, although still preliminary, is the correlation with the record from the Iberian margin. Here I have reported pollen from the core MD2443, and the pollen record from Tenaghi-Philippon, the low resolution and the high resolution. And it's possible to see that, as example, there is a comparable length of the interglacial optimum marked in our record by the wettest period and by the spike in the pollen. Also, the variability during the glacial inception is relatively similar, and it's particularly interesting is this event within the MIS 9C because it has been linked to the overrun of a critical threshold for ice volume, which triggers ice sheet instability, large iceberg discharge, and disruption of the North Atlantic thermohaline circulation. And this similarity suggests that precipitation at our site are influenced by North Atlantic conditions. Also, there is a comparable expressions of the interstadial 9E and 8B, which are well expressed in our record and also in the pollen record from Tenaghi and from the Iberian margin. To conclude, the delta 18 of our stalagmite can be interpreted mostly in hydrological terms and appears to be mostly related to the Haumont effect. The length and the expression of the hydrological terrestrial stages well fits in the regional and extra-regional framework. Indeed, there is a comparable length of the interglacial optimum. There are evidences for increasing hydrological variability during the glacial inception, and potentially this variability can be related to North Atlantic condition and to changes in the ice volume. Also, the particular prominence of interstadials 9E and 8B seems to be regionally significant. And to conclude, quite important things is that the good match with the Auric Lake suggests that it may be possible to improve the lake chronology by aligning lake proxies on the radiometric spiritum chronology. Thanks.
It's not a question, in fact, it's information. Unpublished data that we have to publish quite soon show that the terrestrial equivalent of 9E lasted more or less 9,000 years. Really? Is longer, is from the site, Shackleton site.
Okay.
And is longer than that's shown in MD01 2443.
Okay.
Is longer. It's like a little bit north.
But there are no events in.
There are events, but are not so pronounced.
Okay, and then there is an increase again. Okay.
Yes, as those shown by the MD01 2443.
Good to know. Hope to see the paper soon. Yeah.
More or less 9,000 years of duration.
Okay, good to know. Thank you.
Good morning. This is a collaborative work that we did with Caroline Umenhofer, Mariano Barrientos, and others, where we reconstruct 400 years of extreme hydroclimate using stable isotopes from Iberian tree rings, and also applying nonlinear methods. So our study site, it's Lillo. It's a Pinus sylvestris forest located in the northwest of the Iberian Peninsula in the Cantabrian Mountains. So it's a place very influenced by the Atlantic. The tree ring parameters that we measure were ring width, carbon and oxygen stable isotopes. Main goals of our work here was to assess if stable isotopes have any advantage over tree ring width to reconstruct past climate variability, if we can retrieve different climatic information using nonlinear methods, and how large-scale circulation patterns drive the observed fluctuations in our tree ring proxies. And finally, we wanted to see if historical and documentary records were telling the same story than trees. First step is to know which is the climate sensitivity of our tree ring proxies. In this slide, we can see the ring width on the left, delta carbon 13 middle, and delta 18 in the right panel, and the significant correlations with precipitation with the blue bars, and significant correlations with temperatures with the red bands from October previous year to September current year. What we can see is that the proxy with highest sensitivity to climate, it's delta carbon 13 isotopic ratios with negative correlations with summer precipitation and positive with summer temperatures. Oxygen will have like the same sign here, but it's, the signal is a little bit weaker. While ring width has almost not climatic signal in that side, just like very mild positive correlations with summer temperatures. So the most classical approach to reconstruct summer precipitation variability will be to take some common period with the instrumental data and our tree ring proxies, build a linear model, then validate this model in another independent part, also overlapping with the instrumental period. And when the statistics are good enough, that it will be the case here, we can reconstruct how was hydroclimate for the last 400 years. But in this work, we wanted to do something different to see if we can get like more specific information about seasonality. So what we did, it was a non-linear approach, taking from our tree ring proxies the highest and the lowest years. Once we have selected which are the years with the highest and lowest values in our proxies, we can come back to the instrumental record, in that case aggregate precipitation data, and do composite maps here for these years. And in that case, we can see how the highest years with highest values in our proxies were significantly drier for these composites, as well as the years with lowest values in our proxies were showing significantly wet conditions over the Iberian Peninsula. Next step will be to build like the seasonal cycle. For doing that, we will not use all the gridded data of the Iberian Peninsula. We'll just focus on a mean generated in this box. And we can see how the hydrological cycle looks like for that box from October of previous year to September current year on the grade shading. And then, just like getting the years of high isotopic values, we can build a seasonal cycle for those years in red, as well for the wet years in blue. Whenever these lines are outside the grade shading, it means that the conditions were significant. So what we can see in that case is while the enriched delta carbon-13 values are significant just for June month, for the lowest values, the deplete values of delta carbon-13, the period where we find like wetter conditions, it's much more extended to the full summer, June, July. This approach can be done for all our proxies. So here we have ring width, delta carbon-13, and delta 18. In the first row, we can see the selection of the high, low years, and in the middle panel, we can see the seasonal cycle for precipitation, where in the lower panel, we see the seasonal cycle for temperature. We have already talked about the middle column with delta carbon-13 values. We can take a look at the right column for the delta 18 extreme values, where we can see that this shift in seasonality for the low and high values is even more extreme, with the enriched values showing the dry conditions for late spring in May, while the low values, the deplete values of delta 18 showing the wet conditions for the June-July month. Regarding ring width, although it has like significant values also for June-July temperatures, even if it's not so clear, we can see that the sensitivity is much lower. But in that case, we are able to get also this summer sensitivity that we were not able to see in the linear approach. So coming back on how are atmospheric patterns for these dry years, the years where we were observed these extreme values. So we can see on the on the upper panel, that for the three proxies, we were detecting significantly drier conditions all over the Iberian Peninsula associated with warmer temperatures. All this was more broad on the delta 18 compared with the others. And these patterns were associated with a reduction of moisture coming from the Atlantic that was associated with current large-scale circulation patterns. Same was seen for the wet conditions using the extreme wet years for the three proxies that show like significantly more wet conditions. As you can see, while the ring width show just like some significance here over the Leo side, a little bit there, for isotopes, these wetter conditions for summer months were much more stronger. Once we have demonstrated in the instrumental period that this extreme year method is working, we can explore our paleo record with the same approach. So we establish some thresholds based on the information on the instrumental period, and then we go back in time for the pre-instrumental period, selecting these high and low years for our three proxies. For validating how well we were doing, we used the same approach, doing composites of, in that case, of a sea level pressure gridded data set that is going back to 1500. And what we saw here is that the patterns that we were getting in most of the cases were consistent with the atmospheric patterns that we were observing for the instrumental period. So this was kind of a validation that we were doing a pretty good job in the pre-instrumental period as well. The second validation was using the all-world drought atlas, that it's a Palmer Drought Severity Index gridded product. And while in that case, while we were finding pretty good results and matches on the upper panel for the extreme years showing wet conditions, you can see that it's wet over Iberian. The results were not so clear for the extreme years with dry conditions. Even though we do not observe much wet conditions in the Iberia, it was almost non-significant or just slightly dry. You can see that with the brownish colors on the lower panel. So now was time to assess the frequency of these extreme hydroclimatic events back in time. Thanks to using this nonlinear approach, we were able to do that for the low isotopic values reconstructing summer, mainly June, July, while the high isotopic values were mainly reconstructing conditions in late spring and early summer. We can see that for delta 18 dry May and delta carbon 13 dry June. For validating that, we use complete independent information from historical and documentary sources. Our Mariano Barrientos have like a nice record of rogation ceremonies from the Catholic Church that, depending on the severity of the drought, they have like different levels of rogation. So we can assess that. And very quickly, we confirm the persistent mid-19th century pluvial found in our Turin proxies with documentary sources from Barcelona that show higher precipitation than usual between 1835 and 1875. There was also a 6-year record rainy period unique in the next 160 years. There was also lack of droughts and more frequent severe catastrophic floods, at, for instance, the Santa Tecla flood that finished with 500 deaths. And there were also a higher frequency of extreme events, strong snows, marine storms, and atmospheric convective activity and catastrophic floods. For the dry period, we also found pretty good agreement with our longest dry period, and this was confirmed with rogation historical data from the Toledo Cathedral that showed severe droughts from 1575 to 1800, while almost no droughts were reported from 1800 to 1900. In the late Maunder minimum shown by the star in 1675-1750, also we observed very dry conditions in our early spring reconstruction, and this was confirmed by data from Catholic rogations from Toledo and Zamora and the Ebro Basin that have a very strong influence of the Atlantic. Finally, this drought in the 1877s was also confirmed from some documents, some droughts reported in the Ebro Basin. These kind of droughts were occurring in parallel in the northeast of the Iberian Peninsula, as well as in the northwest, where our tree ring is located, or tree rings are located. And this coincide with a high pressure anomalies over Central Europe, which might produce a blocking situation, preventing the arrival of low pressure systems from the Atlantic Ocean. Finally, at the end of the 19th century, you can see this dry period. This was also kind of confirmed with low rain production in 1800 at the that led to less food and less resources, that led to social conflict and migration, such as the Neo-Galician and Asturian migration to South America. So main key message, stable isotopes can provide distinct information than ring width. Nonlinear methods, as the analysis of extremes show here, can inform us about distinct seasonality in our tree ring proxies. And they are also useful methods to understand better the atmospheric circulation patterns that are driving the climate signal record in our tree ring proxies. and historical and documentary data are complementary and validate the reliability of our tree-ring reconstructions in that case. Thank you.
And your reconstructions seems to me quite robust, but in an area with such a long history of human impact, I was wondering if you have considered changes in land use that could have affected the tree-ring record.
I think that this site, it was not completely pristine in that sense, so there was human intervention, at least for the last years. So this is a factor that should be considered. And so it's not completely a clean record, we can say. But that fact that we are getting like the extremes and validating that with instrumental data, and then we can do that same approach using pre-instrumental data sets completely independent to ours, I think that make that pretty robust. Maybe one of the extremes can be not related to climate, but when you put all of them together, it gets stronger.
Good morning to everyone. I'm replacing Mario Morellon that due to academic duties was not able to come. Mario is leading a group, an international one, working on Lake Butrint sediments. The lake is a lagoon, is a coastal lagoon that is located in southern Albania, not far from the island of Corfu. It's just in front of the island of Corfu, and few kilometers apart from the Greek border. The lake is in an area very well known from a paleoenvironmental point of view, as there are many lacustrine records of Holocene and Pleistocene age. The area around the site is quite interesting because from a biological point of view is a biodiversity hotspot, and from the archaeological point of view, maybe it is even more important in the sense that this small hill, you can see on the left bottom, is the archaeological site of Butrint that was active since the Bronze Age. It was then an Hellenistic and classical town, and it was even more important during the late antiquity period, so in the first centuries of the new era. And Venice ruled the area and built a castle on the top of the hill because it was very important. It was a strategic point controlling the Ionian Sea. The lake is north-south oriented, and it has a tectonic origin. This depression was invaded by the sea at the time of the Holocene sea level rise, and for a long period it remained an open marine bay. The lake is not very deep. At present, the highest depth is 21st meter, and it is that just right in that point that a core was taken named BUT-12. What we can see is that the lake is surrounded by mountains on the eastern side and by two plains, one from the northern side and one from the southern side. These are relatively young deltaic plains. The sediments are mostly laminated, but there are intervals in which the sediments are rather homogeneous, as we can see from this picture. The age model, the first step in assessing the age model was to use cesium-137 and AMS radiocarbon dates on old record. But then my colleagues realized that there were many fast events, turbidites, homogeneous from a sediment point of view, and so they have been removed to obtain a more corrected age model. The age model is still improving, and there is a poster in the poster session, the poster 41, that is dealing with this topic, and we are also going a bit ahead, trying to have a tephrochronology study helping once more in the age model. The sedimentary record has many proxies. Most of them have already published on quaternary science reviews last year. And I just want to draw your attention on the fact that the last turbidites have been related to specific earthquakes events by Aristegui et al. In a very detailed sediment work on the last 300 years. So there was a clear correspondence between these homogeneous events and recent earthquakes, historically documented ones. We well know that the area is a particularly seismic one, and we wonder if homogenites can be taken as earthquake proxies. There are many geochemical data showing differences in water salinity, so in water content, that can be used as climate proxies and helps in defining different sediment units. Going to palynology, the data are still unpublished. We just published a few curves. I just want to make two main points. One is marked by the first line, and it is the decrease of canopods, the older line. So it marks a change around 3,700 years BP. And the second, a strong decrease in canopods. And the second important change is the continuous curve of elder that occurred 3 centuries before Christ era. These are clear changes in the environment and have been used together with other proxies to assess the geomorphological evolution of the area. So we know that in the first unit, the lake was still not a lagoon, but it was an open bay, as evidenced by the presence of marine mollusks such as scaphopods, very high values of canopods that indicate saline environments. And the area was subjected, the area in front of the archaeological site that is marked by the black arrow, the small oval is the archaeological site of Butrint, was under siltation. The siltation had already began, and due to the river that was filling up the Vrinia plain. The following sediment unit deserves some attention because in this unit a lot of not homogeneous levels have been found for a total of 17 centimeters. And we wonder if this can be the sign of the seismic crisis of Corfu Island. There is a historically documented very strong earthquake, 6.8 of magnitude, that involved the island of Corfu and caused a tsunami that destroyed left important traces on Lefkada and on southernmost island in the Ionian Sea. So Butrint is just 6 kilometers far from Corfu. Why not considering this possibility? Of course, the subsidence is still very active in the area, so we should also take into account this fact. There is another period that is worth to be mentioned. We can see that the small promontory in which they settled since the Bronze Age is enlarging. So there is a flat area at the base, and that also the Vrina plain is becoming wider. In this period, of course, there may be different causes for this enlargement, one of which could be extreme events that, for example, are historically documented in central Italy. We have many flood events in the Tiber River, but at any rate, there is also increasing human impact, and so we have also to consider forest clearance as a possibility of this more rapid enlargement of the deltaic plain. This is the period in which Greeks and Romans settled there. But it is in the first 5 centuries of the new era that there is another important change showed for sure by the sediments, and also evident for the geomorphological evolution of the plain and for the features of the settlement. In this period, the Byzantine populations settled there, and there was a connection between the old site and the Vrinia plain that was completely filled up with the houses and fields, and there is a Roman aqueduct connecting the two parts of the town. So again, the siltation is becoming more important, and is definitely closing the lake, the basin to the sea, that now is connected with the sea through the channel of Vivari. What can we say from a climatic point of view? Pollen didn't help so much in defining this, but the chemistry of water and also the mineralogical components helped to define arid conditions during the early Roman, during the medieval climate anomaly, and after the 19th century AD. We are aware of the fact that there are inverse patterns in other parts of easternmost countries. Concerning the humid periods, we know that there were humid periods during the early Middle Ages and also during the Little Ice Age. And again, there is a contrary pattern both in Anatolia and in the Levantine region. So, concluding, I already announced the conclusions. Here we have the interplay of different of different things. We have not just the importance of climate changes, so of climate forcing, of human impact, but tectonics is also complicating the environmental reconstruction, and so it is even more complicated to draw unique conclusions.
Now we move from the continental to marine environment, and this talk deals with the geochemistry of deep water corals as proxy for the ventilation of the intermediate water in the Mediterranean Sea during the Holocene. This is a map of the Mediterranean showing the mid-depth general circulation pattern. As you can see, it's quite complex and it consists of different gyres and eddies. But the general picture here is show like basically the Levantine intermediate water flowing from the eastern Mediterranean towards the western Mediterranean and crossing the Sicilian Straits and eventually crossing the Gibraltar Strait. But why is it important to study the Levantine intermediate water? I mean, I put here three main reasons. Probably the most important is that the Levantine intermediate water represents up to 80% of the Mediterranean outflow water that eventually it has been shown, it has been suggested to precondition the North Atlantic deep water formation. Then the Levantine intermediate water is also known to precondition the formation of deep water in the Mediterranean Sea in at least 3 different sites. And then also for ecological point of view, the Levantine intermediate water has been shown to have a link with the deep water coral ecosystem since it's a carrier of the larvae, for example, and some like strong currents and nutrients. Here is a picture of what we know so far about the deep water coral distribution in the Mediterranean, and it has been, it comes from like basically several cruises that have been taken, carried on during the last, let's say, 20 years, mainly by the Institute of Marine Science in Italy. And of course, this is not the final picture, but this is what we know basically in 2016, and the yellow dots are the living occurrence, and the red dots are the fossil spots of deep water corals. And as you see, this is the Levantine intermediate water, the gray line, and the main living occurrence of deep water corals stay along the Levantine intermediate water path. The sites of the study, so for the presentation I will show some results coming from 2 sites. One is the south of Sardinia, and the other one is sediment core. There are 2 sediment core from the Siculo-Tunisian Strait. So one from the south of Sardinia, 414 meters, and the other one is in the Siculo-Tunisian Strait at 340 meters. And here is a picture of some living occurrence of deep water corals. You see the beauty of some like deep water coral species. In particular, this is Madrepora oculata with some like solitary coral Desmophyllum dianthus. And this was taken during the record cruise, so in the southern Sardinia, and just above the sediment core that we collected. And the sediment core are full of fragments of corals, as I will show you later. And all these, I want to point out all these like gray squares that are the seawater sample that we collected for tracers and especially neodymium isotopes. Both the sites are bathed by the Levantine intermediate water. So this is really the depth of the core of the Levantine intermediate water. So what we reconstruct with the corals are really the physical, chemical component of the Levantine intermediate water, so the changes. And here is an example of the record cruise, so the southern Sardinia. And you can see here is a relatively short core, but for deep water coral it's quite long. Let's say it's 4 meters and something, and is full of coral fragments. It was first X-ray radiographed, and then we did also computer tomography just to check where the fragments were. And then we sliced the core and we picked the fragments of corals, and then we started to analyze these corals. And first of all, we date the coral with uranium thorium. This is like the great advantage of aragonite scleractinian corals that can be precisely dated by uranium thorium. I forgot to say, so the record sediment core covers the last 11,000 years, whereas the core from the Sicily-Tunisian Straits go back to the late glacial maximum. But for this talk, I will present only the Holocene data. We applied the multi-proxy approach, which consists basically in selecting some coral fragments from the same colony and applying different tracers. In this case, we apply lithium-magnesium clamp isotope and stable isotopes for temperature reconstruction, boron isotope for pH, neodymium isotope as a water mass provenance tracers, pair uranium thorium C14 for the ventilation, and then when you combine uranium thorium C14 and neodymium isotope, you have really the full water dynamics. For this talk, I will show only data from the uranium thorium C14 and neodymium isotopes. As I say, so we combine uranium thorium and C14 ages to calculate the seawater delta C14, which following the method of Atkins and Boyle in 1997, which basically consists in calculating the seawater delta C14 from the radiocarbon activity of the coral by correcting the chronological component of the radiocarbon through the uranium thorium ages. The data, so this is the marine curve, delta C14, and the atmospheric curve, delta C14. The data are plotted as like the red symbols represent data from the southern Sardinia, and the blue symbol, the Sicily-Tunisian Straits. As you can see, there's like a bit of variability, but most of the data plots on the marine curve, suggesting well-ventilated condition during most of the Holocene. But at the beginning of the Holocene, so we have most of the data plots on the marine curve. Just at the beginning, just at the enter of the sapropel S1, so the sapropel is a period of time when some organic-rich sediment were deposited mainly in the eastern Mediterranean Sea, so suggesting an anoxic condition in the bottom water. So at the beginning of this sapropel S1 event, we see that the data are lower and plots below the marine curve, suggesting reduced ventilation condition. Then at the mid-sapropel S1, around 8.7 thousand years, we have, it seems that the coral suggests like a reventilation condition in the southern Sardinia. Then we have again like a condition of reduced ventilation, and then finally at the end of the sapropel we have what is like the present day condition of ventilation, so well ventilated in the intermediate water in the Mediterranean. So it's nice to see that this trend followed the C14 decay trajectory, which means basically that the Levantine suggests the Levantine intermediate water was stagnating, and it was evolving following really the decay trajectory. If we calculate now the reservoir, the marine reservoir effect, which is basically the difference between the C14 age of the coral and the C14 age of the atmosphere at the corresponding age, so we have value as high as 800, 700 years, which is quite high. And if we compare this with the record of barium calcium and planktonic foraminifera coming from the Eastern Levantine Basin from Delb and et al. In 2014, we see that these increase in the marine reservoir age correspond quite well to the increase in barium calcium concentration in the forum, and of course at the high insolation maximum. So basically it means that there was like a high river runoff coming from the Nile, and this river runoff was intensified by the African monsoon at this time period, and the Levantine intermediate water seems to respond quite quickly to this change. But of course, in order really to identify or characterize the potential changes in the water mass circulation and water mass sources, we decided to apply proxy or tracers, that is neodymium isotopes, that is a tracers of really like the provenance of the water masses in the Mediterranean in this case. And first of all, we did like a survey of the seawater masses in the Mediterranean. We saw that there are like two different contrasting results: radiogenic value in the Eastern Mediterranean and a less radiogenic value in the Western Mediterranean, corresponding more or less to the salinity pattern. We know that deepwater corals record faithfully the epsilon neodymium of the seawater. This was shown worldwide, and we did also the same exercise in the Mediterranean, and we compare seawater with the cold water corals, and we see that basically all the data plots within error to the seawater epsilon neodymium. So these are the results. So as you can see here, we have basically two end members. One is the values of the modern Levantine intermediate water in the Eastern Mediterranean basin, which is more radiogenic, and less radiogenic in the Western basin. So at the beginning of the subpropel, you have value of from the Eastern Mediterranean, and at the mid subpropel S1, you have value more from the Western Mediterranean. So if we put all together, we see that the value here that is suggesting reduced ventilation condition in the Levantine intermediate water correspond still at value of epsilon neodymium that's really from the Eastern Mediterranean, whereas the mid subpropel S1, we have the coral wealth bathed by well-ventilated water, but suggesting origin from the Western Mediterranean and not from the Eastern Mediterranean. So I conclude with a simple model cartoon. So here is the first is the map with the two sides. So we have, first of all, the normal condition that is basically the present day condition with strong Levantine intermediate water from the Eastern Mediterranean flowing westward towards the Gibraltar Strait. And so you see is the Cyclo-Tunisian Straits and the Sardinia Channel. And we have very well ventilated condition. Then we go into the beginning of the subpropel, and we have reduced condition of ventilation, but still we have value from the Eastern Mediterranean. Then at the mid subpropel, we have basically well ventilated condition, but epsilon neodymium suggests value from the Eastern Mediterranean. So the hypothesis that we suggest here is that the Levantine intermediate water was extremely reduced, probably stopped, and we have value or water masses coming from the Western Mediterranean, and in this case, the Western intermediate water. And then we have again value. Unfortunately, we don't have value of epsilon neodymium because the fragments were very small and we didn't have enough material. But we go to reduce ventilation conditions. So we hypothesize that we basically restart a bit the Levantine intermediate water formation, and then finally we go to the final stage, that is the present day at the end of the subpropel, and is present day condition of the ventilation. Thank you very much. Muchas gracias.
Thanks, Paolo. Very nice talk. Beautiful data. I really like that story. I have two questions. One is regarding At the beginning, you comment that the current corals, the alive corals at the moment, they are following the Levantine intermediate water path. There's any reason for that? It's a matter of nutrient-rich water, temperature, or is turbulence? Do you know why is this happening? And my other question is regarding that figure you just passed where you do the corrections for the carbon edges in base to the uranium, thorium. And there is a data point on the very right side which is above the marine. Is that data relevant? Do you have any explanation for that? This is
okay, so the first question is so the Levantine intermediate water, the correlation with the deep water corals. Why is that? If I say, yeah. So okay, there's no really like a straight one reason for that. I mean, this was like shown in the North Atlantic that the deep water corals are really distributed following the a density range. And so we believe that it's basically the same in the Mediterranean, but of course a different density range. And this is probably consistent with a good density for like carrying the larvae of the corals. And then probably is even strong currents, but this is, I mean, mostly deep water corals are really along the trajectory of the Levantine intermediate water, but there are also other evidence from the North Atlantic, the North Adriatic deep water also, from the strong currents and the carrier of nutrients. So the other question is about this point, basically, that is above the marine curve. I mean, you know that marine curve is a model of, it comes from a model from like the atmospheric delta C14, and basically applying also like an offset. And but I mean, probably I believe this data is this value is true, and it's probably really like a time that was really extremely well ventilated, and so basically there was the reservoir age was no like 400 years as is at the present day condition. This was probably reduced for this very active ventilation of the Levantine intermediate water. But this is just like a suggestion.
Some records show an interruption of subpropel 1 in the middle. Could you place that in the context of the circulation changes that you're seeing?
So unfortunately, I don't have like corals that were dated at 8.2 or something like that. That is normally what is considered the time of the interruption of the subpropel S1 in the Mediterranean. So I don't have really like corals suggest, unfortunately. I mean, we have the cores, and so we are like now repicking samples, and hopefully we will have like a cover of, like a better cover of the subpropel S1.
So what you're seeing now, the change in circulation, is not related to that interruption? Okay.
No, this is really 8.7, so it's before.
Now we move to the Atlantic side, and we are going to see what happened on this side of the Gibraltar Strait and in response to all these changes in the Mediterranean thermohaline circulation that we have seen before. Well, I'm going to focus on this side, 1389. This is on the track. I don't see its pointer. Okay. Well, 1389 is on the way, on the track of the Mediterranean outflow, and it's exiting the Gibraltar Strait and is following the slope of the Gulf of Cadiz. Well, this is a picture profile going from the Alboran Sea to the Atlantic side. This is the location of our site here in the profile. As you can see here, the high saline Mediterranean outflow is going out and is descending down to reach the setting depth here in the Atlantic at 1,000 meters. Then our site is on the way to the Atlantic of this Mediterranean outflow. Well, to investigate the changes in the Mediterranean outflow and the velocity of the MOW along the last 250 kiloyears, we look at the content of sand, the sand content in the sediments. This is the content of fine sand, and we use this proxy to investigate these changes. As you can see here, there are some intervals where we don't see sand in the sediments. It's mainly clay. And that means that the mow collapsed at those times and was probably very weak. Well, in order to check if this sand content is really a good proxy for Mediterranean outflow, we compare with the zirconium aluminium changes that were previously published for the upper part of this record by Bard et al. In 2015, and we see that the correlation is really good. Then we assume that the main changes in the content of sand are related to the speed of the mow. Okay, this is the fine sand. Now we use a logarithmic scale, and note that the scale is inverted. Then the levels towards the top are those levels with very weak mow. When we compare this record with the Asian monsoon, we see that there is a strong correlation between the two records that was already published for the upper 100 kiloyears by Bard in 2015. We assume that when there is weak monsoon, strong monsoon events towards the top, we have really this very low speed of the mow in the Gibraltar Strait. Well, many of these authors have used these records in the Asian monsoons as synchronous changes with African monsoons, and then they are related to shifts, northward shifts on the ITC set in Africa. These events are related to a higher and larger discharge to the Mediterranean, and this freshwater input into the Mediterranean cause Mediterranean stratification and subpropel deposition. Here we compare with varying aluminium records in the Eastern Mediterranean, and you can see a clear correlation between the low speed, low velocity of the mow and the subpropel deposition in the Eastern Mediterranean. Then at orbital scale, it's clear that the main changes in the velocity of the mow are related to Mediterranean thermohaline circulation, especially to the times where the Levantine intermediate water, the production of Levantine intermediate water were very reduced, probably because of this Nile discharge, and also because of the increasing annual precipitation around the Mediterranean, not only the monsoons. Well, of course, this is obviously correlated with insolation. Then the main patterns of our record in Mediterranean outflow are clearly related to changes in the Mediterranean hydrological budget. Well, when we look at details in this record, we see also very nice patterns at millennial scale, especially during the last glacial record, and also in stage 6 and 8. Well, this is the content of sand in the sediments in the Gulf of Cadiz. And you can see when there is at the stadial, Greenland stadials, you can see that the content of sand is much larger, in the interstadials is lower. And it's a clear millennial scale variability that we can see in the mow. Well, this pattern is very clear, but there are notable exceptions, especially during Heinrich stadials. In all Heinrich stadials, you can see that there is a drop in the sand content that representing probably reduced mow or lower speed mow in the middle of the Heinrich stadials. I'm going to talk about this later. Here is a picture of one of the sediments of sections, sedimentary sections in 1389, and you can see clearly that these Greenland stadials, Greenland stadium 6, 5, and 7 are related with high sand content in the sediments, reaching sometimes values of 25% in the sediment. However, in these levels related to Greenland interstadials, in particular Greenland interstadial 5, 6, and 7, clearly represent periods of very weak mow in the Gulf of Cadiz. This is a detail, a picture of the transition from Greenland stadial 6 to Greenland interstadial 5. You can see there's a clear change. There's a contraride layer, sandy contraride layer associated to Greenland stadial 6. Well, we again compare with the monsoons records in Asia, assuming that the Asian monsoon records are probably similar to the African monsoons. And we see that this clear variability is also in the Mediterranean. As you can see here, when there are weak monsoons, during stadial intervals, we have strong currents in the Gulf of Cadiz. When the monsoons are stronger, we have reduced mow in the Gulf of Cadiz. Again, we assume that most of the variability that we see in the Gulf of Cadiz is related to internal changes in the Mediterranean, in particular to changes in the hydrological water budget in the Mediterranean. In stadials, during the stadials, we have, of course, colder winds in the northern margins of the Mediterranean. We have more arid climates around the Mediterranean. We have less inflow from the Nile. Then everything is in favor of a higher rate of deep water formation in the Levantine intermediate water and also in the Gulf of Lions. Then an increased rate of deep water formation or intermediate water formation in the Mediterranean seems to be the reason for these changes in the speed of the mow in Gibraltar. Well, as you can see here, there is an exception to this pattern, and this is really in the middle of Heinrich stadials. In all Heinrich stadials, you have a minimum or a weakest monsoon events, and at these times in the middle of Heinrich layers, Heinrich stadials. But in the outflow, we see a decrease in the outflow. We see a lower speed in the outflow, really in the middle part of the Heinrich stadials. And the reason is why. I mean, in the Heinrich stadials, we know that we have really arid climates, and then we probably expect higher speed of the current, but we see the opposite. Well, we compare with a previous record that we have inside the Mediterranean, and we see that there is also some freshwater influence in the middle of Heinrich stadials that we can compare with the Balearic Islands, and we see depletions in the delta within in this region. And this is the time when we see this decreased speed in the mow. Well, here you can see really the high sand content on the upper part of the Heinrich stadial 5 and the lower part and the weak mow in the middle. Okay, well, I'm going very fast because I have only 1 minute or maybe no more time. Just to look at what happened during the last deglaciation in Heinrich, during Heinrich event stadial 1, we see an increase in the grain size, stronger mow, really after 16.5. This means it's in the last part of the Heinrich stadial 1, not in the first one. In the first phase of the Heinrich stadial 1, we see only a small mow. Well, I'm going to finish now. The main thing I want to say is that especially during at glacial times, most of the fresh water is coming from the north, not from the monsoons. Of course, it's coming from the north. We have a strong freshwater input from the Atlantic during the glaciation. This fresh water is coming to this region and then flows towards the Mediterranean through the Portugal current. The other source of fresh water may be the Alps, here coming to the Adriatic Sea and to the Mediterranean, to the Gulf of Lions. And of course, there is I'm going to jump this. And of course, there is also a possibility for freshwater source coming from the southern margin of the Fennoscadian ice. It's going to the Caspian, the Black Sea, and entering the Mediterranean. Then this freshwater probably coming to the Mediterranean produce also a reduced mow in the Atlantic. Thank you.
If I understood well, you proposed that the fishery, the surface fishery that we have during the Heinrich, it potentially might also come from ice melting from the Alps. So that, well, I have two questions regarding that. Two. If we know that we have very cold conditions on land and in the sea during these Heinrich events, so why do you think we will have a melting at that moment in the glaciers in the Alps, is the first question. And the other question is, did you try, if there is pressure coming from the Alps, I will expect also a strong signal, for instance, in the Promise site. Did you try the exercise to compare the isotopic anomaly in the Promise site compared with Minorca, with Alborán, whether we can see a spatial change regarding this? This is the question.
Yeah, I traced this anomaly from the Atlantic to even to the east. In the Eastern Mediterranean, there are some published records that in last year, but I don't know exactly the H scale is okay or not. But in the south of Sicily, there are very nice records published by Sprovieri, and the depletion in the Delta 18 is much higher than in the Alboran Sea. Also, we see this in the Gulf of Lions. In the Gulf of Lions, the surface waters are mainly Mediterranean because the salinity is 38. And even in the Gulf of Lions, you see this anomaly in the Delta 18, and also, of course, in the Adriatic Sea. The records for the Adriatic Sea are very poor because the resolution is very small. But it seems that the anomaly in the Delta 18 is coming from the Mediterranean. But it's sure that the main evidence we have for this freshwater origin is also the Atlantic, because we have along the Portuguese margin, we have a strong depletion during Heinrich Stadials, well, all Heinrich Stadials, but in particular in Heinrich Stadial 1. Then the source of the freshwater is unknown. I know it's very different to estimate the changes in the speed of the MO is very different, the response, if the source of fresh water is in the Atlantic or the Mediterranean, based on the models that were run by Mike Rogerson. But still we don't know exactly where is this fresh water coming from. Yes, in the Alps. Well, the main thing, and this is, the last part of my talk that I couldn't finish, as usually. In the Alps, there are records of glaciers, Alps glaciers, and then they have a retreating ice between 18 and 16.7. That is really the time when you see a strong depletion in the delta within the Mediterranean. But it's the same in the Atlantic. Then, of course, it's different to know if this is really the source of the fresh water. But there is a glacier retreating between 18 and 16.5, which is really the middle of the Heinrich Stadial, and after 16.5 is like a pre-advance of the Alps, of the Alp glaciers. Of course, dating in the moraines and everything is not so good like carbon-13 records.
In your third from last image, you showed an anomaly at 4.2 kABP. And I'm wondering, you have labeled as contourite. Could you please review that image for us?
Which one?
Go right there. Yeah, the lower. Oh, it's your Del 018 scale. I see.
Yep.
You have these anomalies in the Holocene.
Here. This one. This one, you mean?
No, I was curious about the one at 4.2.
Here?
You're in the lower of your three scales? Your Del 018?
Well, I don't know exactly if this, because it seems that this anomaly in the between 6 and 10 may be something. I mean, probably because of the mixing that happens between the Mediterranean outflow and the Atlantic inflow in the Gulf of Cadiz. But I don't know exactly if the other two are significant or not.